Hello everybody, this is Mr. Fasoni. In this video we're going over chapter 4.4. Remember that chapter 4 is polynomial functions, and chapter 4.4 specifically is about factoring polynomials. So let's get going with our goals. So our main goal in this section is to factor polynomials. And we're also going to be using something at the end of this section called the Factor Theorem, which rises right out of the Remainder Theorem. So we'll be building off that to build the Factor Theorem. It's really just a result of it. So let's get right into it. So concept 1.a, factoring polynomials. So previously we factored quadratic polynomials, but we can also factor polynomials that have a degree greater than 2. We can factor polynomials completely using techniques that we have previously learned. A completely factored polynomial is written as a product of unfactorable polynomials with integer coefficients. So just like factoring a number, if I factor 24, I can break it into 4 times 6, and then 4 breaks into 2 times 2, and 6 breaks into 2 times 3. So 24 is effectively 2 times 2 times 2 times 3. Or in condensed form, I could say it's 2 to the third times 3. The same idea happens here with polynomials, but instead of using a tree structure because it would be unwieldy, we just break these into different parentheses that are all next to each other. So we'll see that in just a second here. So we're going to factor each polynomial completely. I'm going to start off with this one in the upper left. I've got x to the third plus 10x squared plus 24x. Well, if I look at this, I'm going to zoom in a little bit so I can write a little bit more. If I look at this, I'm just using the ideas from Algebra 1 here, or even possibly before. I can pull a greatest common factor out of all 3 of these terms. My coefficients are technically 1, 10, and 24, so I'm not going to be able to pull any numbers out, but I can pull an x value out of all 3 of these terms. So I'm going to pull an x out, and I'm left with x squared plus 10x plus 24 inside the parentheses. From there, I can factor this quadratic just like I would in chapter 3. So I can either use what we deemed the X box factoring method, which may or may not work, or I can try using the quadratic formula. So I'm going to use a quadratic formula in this case. So I just need my a, b, and c values. My a is 1, my b is 10, and my c is 24. If I plug those 3 values into my quadratic formula, I'm going to get negative b, which is 10, so negative 10, plus or minus the square root of b squared, that's 10 squared, minus 4 times a times c, all over 2 times a. I'll work this through. It's going to be negative 10 plus or minus the square root of, well, 10 squared is 100. 4 times 1 times 24 is 96. So 100 minus 96 over 2. I'm going to go down a level and rewrite this one more time. It's going to be negative 10 plus or minus the square root of 4 over 2. Well, the square root of 4 is just 2, so it's really going to be negative 10 plus or minus 2 all over 2. So I can rewrite this, zoom in again, getting kind of messy here. Negative 10 plus or minus, let's clean this up. Plus or minus 2 over 2. Well, negative 10 plus 2 is going to be negative 8. Negative 6 for my 2 values. I'm going to rewrite it over here. The factored form will be x minus negative 4, so plus 4, and x minus negative 6, so plus 6. And then lastly, I bring down that x value. And what I'm left with here is my fully factored polynomial, x times x plus 4 times x plus 6. And those are my 3 factors. All right, let's jump forward to this one. 5y to the 6th minus 125y to the 4th. Again, I'm going to look at this and go, okay, well, I've got coefficients that are both multiples of 5. So I'm going to factor out a 5 to start. I'm going to zoom in again here so I have some room to work. So I'm going to factor out a 5 to start. And then if I compare y to the 6th and y to the 4th, I can factor out y to the 4th. So that's going outside of my parentheses. What I'm left with inside is just y squared minus 25. Well, at this point, again, it's a quadratic. I could use the quadratic formula with an a of 1, a b of 0, and a c of negative 25. If you want to go that route, that's fine. But you can also, if you happen to notice this here is a difference of squares in the form a squared minus b squared, which I can rewrite as a plus b times a minus b. So if I see that, that means I can factor this y squared minus 25 into two pieces. The first piece is going to be y plus 5, and the second piece is going to be y minus 5, or vice versa, whatever order you want. And then I'm going to bring down the 5y to the 4th. And again, I am fully factored. All right, let's jump to the last one here. So again, I'm going to look to see if I've got a GCF. If I look at my three terms, I've got 6, 24, and 24 for my coefficients, which means I can factor out a 6. And then I've got x squared, or not x squared, z squared, z to the 1st, and z to the 0 power. So I can't factor out any z's. But factoring out the 6 already simplifies things a lot. I have z squared minus 4z plus 4. And again, what we result in here is a situation where our quadratic can be factored. Now, again, I could look at this and go, okay, well, I've got an a value of 1, a b value of negative 4, and a c value of positive 4. I can plug those into the quadratic formula, figure out my x values, and then flip the signs when I put them into the factors like I did up here above. But I can also notice that this is a perfect square trinomial. Since this is a perfect square trinomial, I know it's going to factor to z minus 2 squared. So now I factored it down and I have 6 on the outside times z minus 2 squared. Another way I could write this, if I didn't want to save some room, I could write it as, if I could write correctly, 6 times z minus 2 times z minus 2 again. The first way is technically more proper because the repeated factor is written as a square versus as the multiplication of two duplicates. So for the basics of factoring, what that means is that I can always start off by trying to get out a GCF. If I can get a GCF out of it, then next I might have some kind of quadratic to deal with. And then once I get a quadratic, I can either use the quadratic formula, use that X box method that we talked about, or if I happen to see a special quadratic like a difference of squares or a perfect square trinomial, then I can use those patterns to break them down as well. If you don't happen to remember the special quadratics, the formulas for them, you can always fall back to the quadratic formula, and that will allow you to factor any quadratic. All right, so let's move forward. So sometimes we have GCFs, sometimes we have other situations. So in chapter 3, we talked about factoring a difference of squares in the form a squared minus b squared. And similarly, there are patterns for factoring both sums and differences of cubes. So instead of second powers, we're looking at third powers. So we have these two formulas here. One's called the sum of cubes and one's called the difference of cubes. There's really only one thing that's different between the two of them. In the sum of cubes, I'm adding two cubes together, and in the difference of cubes, I am subtracting a cube from another cube. But if you look at these patterns, they look effectively the same. Everywhere I've got an A, I've got corresponding A's in the other side of the equation, and same with B's. They're all kind of in the same structure. The only differences between the two, and I'm going to get rid of these little orange things because it's going to add some confusion. So let's clean that up really quick. The only differences we really have is if we look at the signs. If I'm doing a sum of cubes, I have the same sign here, then I have the opposite sign, and then I've got a positive sign. If I'm looking at the subtraction with the difference of cubes, I'm starting with a subtraction sign or minus sign. I have the same sign there, a minus. I've got the opposite sign, a plus, and then I have a positive sign. There's a little way to remember that. If you just look at whatever your sign is, whether it's addition or subtraction for the sum or the difference, the first sign is always going to be the same. The second sign in the pattern is going to be the opposite. And the last sign is always going to be positive. So you've got same, opposite, and always positive. Or in other words, you've got SOAP. Some people find this helpful for remembering it. Other people just memorize the patterns because there's only two of them. But just remember, you have the same structure. You've got A and B in the first parentheses with the same sign between them as the original sign. And then you've got A squared, AB, and B squared. And the signs between those terms are going to be opposite for the first one of the two and always positive for the second of the two. So let's see this in action. Goal 1B, factoring a sum or difference of cubes. So the first one we have is factoring x to the third minus 64. And we want to factor it completely. Well, if I look at this, I go, okay, well, I've got a third power here and I've got a third power here. So my a to the third is x to the third, which means my a is equal to x. For 64, I got b to the third is 64, which means my b value is 4. Now, I don't expect everybody to know their third powers, but it is helpful to kind of have a list. So let me write those down really quick. 1 to the third is, of course, 1. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. Then we've got 6 to the third, which is 216. 7 to the third, which is 343. 8 to the third, which is 512. 9 to the third, which is 729. And finally, 10 to the third, which is 1,000. You don't have to memorize these, but it is helpful to have a little chart or some kind of table that you've made that has these for reference. Because if you don't recognize a third power, then you might miss out on being able to factor a difference or a sum of cubes. So I've got my a and b values. Once I've got my a and b values, I can factor this quite quickly. So x to the third minus 64 is going to be equal to my a value minus my b value. So a value is x minus b value 4. That's my first parentheses. And then my second parentheses is going to have a squared, ab, and b squared. And remember the signs, the first one's the same, the second one is going to be opposite, and the last one is going to be always positive. So this factors into x minus 4 times x squared plus 4x plus 16. Okay, let's try another one. This one's a little bit more complex. I've got negative 16x to the fifth minus 250x squared, and we want to factor that completely. So very quickly, you'll notice, and actually, I don't know why I'm writing this out. I'm just going to talk about it on the text here. I've got negative signs in front of both of these. So if I'm going to look at this, I want to see if I can factor out a GCF first. That should always be my first step with any polynomial, because getting out a GCF is just going to reduce the complexity of what you're left with and hopefully make it easier for you to figure out what you're trying to factor it into. So I'm going to factor out the negative sign, and then I look at 16 and 250. Well, I know they're both divisible by 2, so I'm going to factor out a 2. And then I've got x to the fifth and x squared. So I'll factor out an x squared. I do all that, and then what I'm left with inside the parentheses is going to be negative 16 divided by negative 2 is 8. X to the 5th divided by x squared is x to the 3rd. Negative 250 divided by negative 2 gives me a positive 125. And then x squared divided by x squared, the x's go away. So now I've reduced the complexity of that stuff in the parentheses still, that polynomial in the parentheses. And sure enough, if I'm looking at this, I see that my first term, 8x to the 3rd, well, 8 is a perfect cube, and so is x to the 3rd. So I've got a to the 3rd equals 8x to the 3rd, which means my a value is 2x. And then if I look at 125, I've got b to the 3rd equals 125, which means my b value is 5. So I've got a sum of cubes. So again, I can write this out and finish up my problem. I factored out a negative 2x squared, so that's going to be negative 2x squared. And then 8x to the 3rd plus 125, that piece there is going to factor into 2x plus 5 times 2x squared, which is going to be 4x squared. 2x times 5 is 10x. And 5 squared is 25. So then I put my signs in. I've got an opposite sign and an always positive sign. And now I've got everything factored. So I'm going to take this factored form here, and I'm just going to rewrite it down at the bottom. And now I've got my fully factored polynomial. It factors into negative 2x squared times 2x plus 5 times 4x squared minus 10x plus 25. All right, let's jump forward to our next concept. Concept 1c, factoring by grouping. So sometimes we can't factor out a single monomial using like a GCF, nor do we have a special polynomial that we can see, like a difference of cubes, a difference of squares, perfect square trinomial, etc. So another way we can attempt to factor is by grouping. So sometimes we'll have a situation where we've got, maybe 4 terms, maybe 6 terms, some number of terms, and we'll notice that the first value, or the first 2 values in the polynomial can both be divided by the same value r. And then the second 2 terms can both be divided, or both have an s factored out of them. So what we do is we end up putting parentheses around the RA plus RB part and the SA plus SB part, and we create RA plus RB equals, or I'm sorry, RA plus RB plus SA plus SB. So the second part here on the right, then I begin my factoring. I factor out an R from both the first terms and an S from the second pair of terms. So RA plus RB plus SA plus SB ends up being R times A plus B plus S times A plus B. Finally, I can go from this form here, I guess I'm repeating this with the way it's written, R times A plus B plus S times A plus B, I can rewrite that as R plus S times A plus B. I should probably change my colors because I want to show how this actually works. What we effectively have here is the FOIL method. It's just spread out. If we think about the FOIL method, it's first times first, R times A. Well, there's my first times first on the left. Outer times outer, R times B. There it is on the left again. Inner times inner, S times A. There it is again. And then finally, last times last, S times B, is right there. So I've just taken my FOIL method and I've reversed it. I started off with this polynomial with 4 terms up here on the top. And at the bottom, by the time I was done, I had turned it into 2 binomials that are being multiplied together. So I have reversed the FOIL method. And once I reverse the FOIL method, I've actually split it into 2 pieces. Now this might be a little abstract, so what I'm going to do is work one out. So it'll be a lot more straightforward to see if we actually have some values in there. So I've got, we want to factor x to the third minus 2x squared minus 9x plus 18. Well, what I'm going to do then is I'm going to group these. I'm going to group x to the third minus 2x squared together. That's going to be my first piece. And then I'm going to have my second piece. It's going to be negative 9x plus 18. Oops, I think I deleted my second parentheses. And then in the middle, just to keep track of what's going on, I'm going to place a plus symbol. So now I'm going to treat these like 2 separate little problems where I'm factoring out a GCF. And these should be pretty straightforward to do. So if I look at the first one, I've got x to the third minus 2x squared. Well, I've got an x to the third and an x squared. I can factor out x squared from the first one. And on the inside, that will leave me with x to the first minus 2. So far, so good on that. So let's go over to the right side and see what I can factor out on these. I've got negative 9x and positive 18. Well, 9 and 18 are both multiples of 9. So I'm going to factor out a negative 9. If I factor out a negative 9, negative 9x divided by negative 9 gives me x. Positive 18 divided by negative 9 gives me negative 2. From there, if you notice, now I've got, I kind of changed the color coding. I've got x minus 2 on the inside of the parentheses. That's going to be one of my terms. And on the outside of my parentheses, I've got x squared minus 9. That's going to be my other expression. So I've now factored this into x squared minus 9 times x minus 2. Now we're almost done. I guess I should show the connection with the FOIL method just one more time, though. Remember, this is the reverse FOIL method. X squared times x, that's my first. My outer would be, I don't think yellow is going to work. Outer would be x squared times negative 2. It's right there. Inner, negative 9 times x. That's going to be right there. And last is going to be negative 9 times negative 2, which is right there. So I've undone the FOIL method. Now, we're not quite done yet. I've got x squared minus 9 times x minus 2. Notice that this first part is a quadratic. So again, I can factor it using the quadratic formula with the a value of 1, b value of 0, and the c value of negative 9. Or I can just notice that this is a difference of squares, and it's going to factor into x minus 3 times x plus 3. And then I'm going to bring down my last piece, x minus 2. And now I'm fully factored. All right, let's move forward. Concept and goal, 1.d. Polynomials in quadratic form. So sometimes we have higher degree polynomials that are effectively quadratics in disguise. So what the heck do I mean by that? Quadratics in disguise. Well, let's try this problem out and see what's going on here. I've got 2x to the 13th power plus 10x to the 9th plus 8x to the 5th. Some big polynomials here, or some big high degree polynomial. So what I'm going to do is I'm going to factor as much out as I can. I've got even numbers for my coefficients, so I can definitely factor out a 2. 13th power, 9th power, and 5th power. Well, I can get a 5th power out of all 3 of them. So I'm factoring out 2x to the 5th. What I'm left with is x to the 8th, plus 10 divided by 2 is 5. X to the 9th divided by x to the 5th is x to the 4th. And 8x to the 5th divided by 2x to the 5th leaves me with 4. So I factored it down now to x to the 8th plus 5x to the 4th plus 4. Okay, well, this is technically a quadratic, the way it's going to function at least. It's not a second-degree polynomial, it's an 8th-degree polynomial. So I don't need, it's like an octet or something like that. But if we think about these terms, x to the 8th, x to the 4th, using what we know about exponents, I can rewrite x to the 8th as just x to the 4th squared, and x to the 4th is effectively, well, this is a little bit redundant, but it's x to the 4th to the 1st power. So what I effectively have, instead of ax squared plus bx plus c, I've taken these exponents, I've just multiplied them by 4. I've got ax to the 8th plus bx to the 4th plus c. So the nice thing about quadratics is that we can have higher powers. As long as they fit the pattern for quadratics, we can treat things like x to the 4th as we normally would treat x. So again, this is going to be, this ax to the 8th is actually ax to the 4th squared plus bx to the 4th to the 1st power plus c. In the standard form of the equation where I have normally an x, I've just got an x to the 4th in its place, which means I can treat this just like a quadratic, which means I can use the quadratic formula if I want to factor it. My a value is 1, my b value is 5, my c value is 4, and I can plug those in really quickly. Negative b plus or minus b squared minus 4 times a times c all over 2 times a. If I do the math very quickly on this, it's going to be negative 5 plus or minus 25 minus 16 over 2, which is really going to be negative 5 plus or minus the square root of 9 over 2, which is negative 5 plus or minus 3 over 2. That gives me 2 values. Negative 5 plus 3 is negative 2 over 2. Negative 5 minus 3 is negative 8 over 2. Well, negative 2 over 2 is just a negative 1. And negative 8 over 2 is a negative 4. So my x values are negative 1 and negative 4. If my x values are negative 1 and negative 4, then I can rewrite this. Remember, I factored out a 2x to the 5th already. I can rewrite this as 2 factors. The negative 1 becomes a positive 1. The negative 4 becomes a positive 4. And instead of an x like I normally would have, I just have an x to the 4th instead. And if I multiply this back together, it'll take me back to where I was at. X to the 4th times x to the 4th is x to the 8th. X to the 4th times 4 is 4x to the 4th. 1 times x to the 4th is another x to the 4th. And finally, 1 times 4 is 4. If I combine all those terms, it's going to be x to the 8th plus 5x to the 4th plus 4. So I can factor this 8th degree polynomial just like a quadratic because it has the same structure as a quadratic. But in the end, my answer to this problem, because I'm factoring, is x to the 2x to the 5th times 4x. I can't talk apparently. Let's try that again. 2x to the 5th times x to the 4th plus 1 times x to the 4th plus 4. All right. So that's goal one, or concept one. Concept two is going to be pretty quick. It's just an outcropping or a result from the remainder theorem. And this is called the factor theorem. So in the previous section, we discussed the remainder theorem and found that when dividing a polynomial f of x by x minus k, then we would get that f of k equals r, where r is the remainder when we divide by that linear function x minus k. So a special case of this is what's called the factor theorem. It states that if the remainder is 0 when we divide f of x, which is our dividend, remember, by x minus k, then when I evaluate that function k at 0, or I'm sorry, then when I do evaluate that function k, I will get a value of 0 as well. And what that all means is that x minus k must be a factor of the original function. So for example, if I'm doing some math in 5th grade, 6th grade, 12 into 384, I can go through this. 12 times 3 is going to be 36. Subtract, I get 2, bring down my 4, and then 12 goes into 24 2 times. I multiply through, and sure enough, I get 0. So whenever I divide something and I get a remainder of 0, that's saying that the number 12 is a factor of 384. Or in other words, 12 divides into 384 evenly. You may have heard that. Divides evenly. In other words, it leaves no remainder, no decimal, no nothing. It's a nice clean division. That's the same thing that's happening with the remainder theorem or the factor theorem. If I have a remainder of 0, then that means the polynomial, the linear polynomial that I'm dividing by, is a factor of the larger polynomial, the dividend, because my remainder is 0, or divides evenly. Let's go ahead and try this out. We want to determine whether x minus 3 is a factor of f of x equals x squared plus 6x minus 12. So I want to determine whether that will divide into that evenly. Well, I can use long division to do this if I want. X minus 3 into x squared plus 6x minus 12. I can do that. I can do my long division. It'll take a little bit of time. It'll be messy. Or I can just go straight into my synthetic division. K must equal 3. And if k equals 3, then I can bring down all these also. X squared is 1. 6x is 6. Negative 12 stays negative 12. And I can just burn through my synthetic division very quickly. Bring the 1 down. 1 times 3 is 3. 6 plus 3 is 9. 9 times 3 is 27. And then if I add those together, negative 12 plus 27 is positive 15. And at that point, I'm done with my synthetic division. I've got my quotient, and I've got my remainder. Well, by the remainder theorem, or by the factor theorem, I mean, since my remainder is not 0, that means that x minus 3 is not a factor. So it's not a factor of the original function, x squared plus 6x minus 12. It did not divide evenly. It left a remainder. It's as simple as that. Let's try it again with this other one. We're going to determine if x plus 3 is a remainder of, this is a bigger polynomial, 2x to the 4th plus 10x to the 3rd plus 11x squared minus x plus 6. Well, I can go through all that work to do long division, but I don't want to do that because I'm lazy. So I'm going to use synthetic division. K equals -3 this time. Bring down all those coefficients, 2, 10, 11, -1, and +6. At that point, do my synthetic division stuff. Bring down the 2. It's the only thing I bring down. Everything else I'm either going to be multiplying or adding. 2 times -3 gives me -6. 10 plus -6 gives me +4. 4 times -3 is -12. 11 plus -12 is -1. -1 times -3 is +3. -1 plus 3 is +2. And 2 times -3 is -6. Finally, I add those together and I get a 0. And I'm done with my division. Again, everything from the left up until the very last value is my quotient, and then that last value is my remainder. Since I'm trying to determine if it's a factor, all I really care about is the remainder. And sure enough, since my remainder equals 0, x plus 3 is a factor. So we found that it's a factor. Now, again, we can check these if we want to using the other aspect of the remainder theorem as well. I could technically take my function. I'm not going to do this here, but I could take my function and I can plug in my k value, which would be -3, and do some calculation in the function, evaluate it, and whatever that gives me at the end is going to be my remainder. So in this situation, if I were to do the calculations, like I said, I'm not going to because it's a little bit time consuming. If I plug in a -3 into my function, my remainder will be 0, or my output of the function will be 0. So that's another way to check. Use what you learned about the remainder theorem, use what we learned about synthetic division, and as long as that remainder is 0, then by the factor theorem, it is a factor, or it divides evenly. All right, so let's put this all together in the last goal here. Factoring a polynomial, we want to show that x minus 2 is a factor of f of x equals x to the 4th minus 2x to the 3rd plus x minus 2. And then we want to factor that polynomial completely. So my first step is I'm trying to determine if x minus 2 will divide into x to the 4th minus 2x to the 3rd. Be careful here. I'm missing a second power, so I have to put a placeholder in there. Into that function evenly. Now, you don't have to write out long division like this every time. I just do this to show the relation. If I were doing this and not teaching it, if I just wanted to do it quickly, I would just write my k value and write my coefficients and make sure to keep that placeholder for 0 or for x squared in there as well. But I want to make sure that everybody sees exactly what I'm doing. So I get k equals 2. I'm going to bring down all 5 of these coefficients. I get 1, -2, 0, 1, -2. It's kind of repetitive. That's interesting. I'm sure that's meaningful. Let's see here. So I'm going to bring down that 1. Remember, the first value always gets brought down. Then it's just multiply, add. Multiply 1 and 2, I get 2. Add -2 and 2, I get 0. 0 times 2 is 0. 0 plus 0 is 0. 0 times 2 is 0. 1 plus 0 is 1. And 1 times 2 is 2. -2 plus 2 is 0. And again, at this point, I've got my quotient and I've got my remainder. So that's definitely a factor. So I can definitely divide out x minus 2, right? So in other words, x to the 4th minus 2x to the 3rd plus x minus 2. I can factor it a little bit. I can pull out x minus 2 And what I'm left with is my quotient. Remember, my quotient is all up here. I've got a negative or a positive 1, that's a 1. This 0 is 0x. This 0 is 0x squared. And then this 1 is x to the third. So I've got x to the third plus 0x squared plus 0x plus 1. I can get rid of the zeros, and it's really just x to the third plus 1. All right, I've simplified things a little bit. I've got a less nasty looking polynomial, and it's a degree lower. It's a third degree polynomial. Well, at this point, it goes really fast because x to the third plus 1, that is just a special cubic. It's a sum of cubes. So x to the third plus 1, I can rewrite as x plus 1 times x squared minus x plus 1. I've broken that sum of cubes into two pieces. And lastly, I can bring down the other piece, x minus 2. And now I've fully factored this polynomial. X to the fourth minus 2x to the third plus x minus 2 factors into x minus 2 times x plus 1 times x squared minus x plus 1. And now it's fully factored. So last little bit, just a recap. We've got all these different ways to factor. If I'm trying to factor a polynomial, my first step, at least what I would do, is look for a GCF. Any GCF I can pull out of a polynomial is going to make it just simpler to deal with. So pull a GCF out, and then what you're left with could be a variety of things. It could be a special quadratic or a cubic. It could be a quadratic, or possibly or a disguised quadratic, or it could be something that needs the grouping method to be factored. So I could be left with some kind of 4 or maybe a 6-term polynomial. So that's from step 1. Well, step 2 then, if I've got a special quadratic or cubic, I can follow the patterns. If I don't remember the patterns for quadratics, for any quadratic, I can either use the X box method, which should hopefully work, but if it doesn't, then you might have to go to the quadratic formula. I always recommend using the quadratic formula because it's going to be it's going to give you a result every time for factoring. If it's not a quadratic, if it's a 4 or 6-term polynomial, or a higher degree that can't be factored anymore, it's not a special cubic, then your method for solving that would be to use the grouping method. And remember, that's just reverse FOIL. So those 3 methods should allow you to break down your polynomial into smaller pieces to be fully factored. All right, so I'm going to go ahead and stop there. I'll be putting this up in just a minute. Hopefully this will be helpful in the review for the final, which will be in a few days. If you need anything, always feel free to reach out to me. See you guys later.